And the objective is to show you that once you pass it through a system, okay, it's very simple to understand code. You are designing a filter. This is in the frequency domain. So in frequency domain, it's more convenient to visualize what is happening. In frequency domain, an h of n, in frequency domain, the output. But if you look at these things in time domain, it's not able to really figure out that what is happening. For example, if I say, so x1 is the signal, so I say plot x1. So this is the signal, that's a random signal, it's a random noise, and then I hold on and I plot y comma red, and y is the output. So this is the output signal. It is changed, obviously it is changed, and there, as you see that so once you have partial overlap, so you have garbage and then again you have partial overlap. But here is the signal. Though the signal has removed, you can see it's high frequencies, but again it's not really able to exactly figure out what system has done to your signal. It is only the frequency analysis which will tell you more about what is happening in your system, how good is your filter, what you intend to do, is that happening or not. So frequency domain analysis is good and it's very convenient. So as far as the designing is concerned, you can design low pass, high pass, band stop filters and multi-band filters, and just think of anything you want, but it got to have something with frequencies, because in this course, in the first part of the course, we are only learning frequency selective system. You say, I intend all these frequencies to pass and rest of the frequencies to stop. Okay, this is a low pass. You say, I want all these frequencies. Remember, pi corresponds to the highest frequency in the signal, and it relates to fs over 2. Okay, for real signal, whatever you see on this side, you see the same thing on the other side. So in your book, you only show spectrum from 0 to pi and not from minus pi to pi, because remember, for a real signal, Fourier transform is symmetric. It obeys the Hermitian symmetry, that its magnitude response is symmetric around the axis. So you don't plot it. Why to waste space, because you're going to see the same thing on this side. So in this book, whenever a real signal or a real system, it will only show you half of the spectrum, because rest of the spectrum is similar to this spectrum. So the important is, again, this is a high pass filter. It will pass these frequency content, it will stop the other. This is band pass, it will pass a band of frequencies, and this is band stop. It will stop this particular band. There may be a particular frequency which you want to stop. You say, I really want to only filter out this frequency. So you want a filter which is 0 at this point, and then it is 1. Or you may want to stop several frequencies. You say this, okay. So you say, I don't want these frequencies to pass and I don't care about the other. Or it may be reverse. You say, I only want these frequencies to pass and I want to stop the other. So it could be anything you want that but it's best, the designer's best visualization is in the frequency domain, that you say, this is what I want in frequency domain, and then you design. So this brings us to a few examples of the Fourier transform, and this is again the theoretical part of the chapter, where you need to learn that how to apply the formula and just feeling comfortable with this. So for example, this is a function a of magnitude n. So it runs for negative value as well as for positive value. So you can break it down into two parts. It is a of n, u of n, plus a of minus n, u of minus n minus 1. It is this part with negative, because once you take modulo of this, for negative n, it will be positive. So this a of n, u of n is for a less than 1, it is this function. Okay, it is function which is going in both direction. So this is an even function. So what do you know about even function? Its Fourier transform should be real and even, because it is real and even. A of n is real and even, so its Fourier transform should be real and even, but it's non-causal. Though it's an IER, and you can say that it's an IER, it is real and even, so it will have zero phase, but you cannot realize it. Why? Because it requires all the future samples. It's non-causal because it requires all the future samples and all the past samples to compute an output sample. So it's not really a reliable system, but this is how you compute its Fourier transform. A of n u of n plus a of minus n u of minus n minus 1. You put a of n u of n in the formula. And formula says x of n exponential minus j omega n. Okay, so if I compute the Fourier transform, I say I know the formula for Fourier transform is x of n exponential minus j omega of n. N goes from minus infinity to positive infinity, x exponential j omega. Okay, so we put both parts. This part says a of n u of n, a of n u of n here. Okay, and then this separately. So let's first compute the Fourier transform of this. So this is a of n u of n exponential minus j omega n, and goes from minus infinity to infinity. This can be rewritten as, because this is u of n means that it is running only from 0 to positive infinity, so you change this to 0 to infinity. And then you can rewrite this a n here as exponential minus j omega raised to the power n. And now you can use that formula. Alpha of n is 1 over 1 minus alpha, so 1 over 1 minus a exponential minus j omega. This is a very interesting expression. This is if a of n u of n, only just you are dealing with a of n u of n, then this is the Fourier transform. 1 over 1 minus a exponential minus j omega, provided magnitude of a is less than 1. This, if you take magnitude of this, it will give you the magnitude response, and if you compute phase of it, it will give you the phase response. And remember this, I have already told you a of n u of n is what? It is a system which you can implement with how many multiplications and addition? 1. It is really this system, y of n is equal to a y of n minus 1. So it is this system. This is the frequency response, because looking at this, I am not able to figure out what the system will do to my signal. But if you plot the magnitude response, you will find out that it will do something like this. So it is basically a low pass system. It will be a low pass system. A of n u of n is a low pass system, and if you only plot the magnitude, but interesting is the phase. What will you get? What do you expect to get if you plot the phase? A linear phase or non-linear phase? This is an IER, a non-linear phase. If you plot, you'll find a non-linear phase, a non-linear phase response. But coming back to this, so this is this part. Now you compute the same thing for the other part. This part is running from minus infinity to minus 1, right? Right, because it is minus and minus 1. Minus and minus 1 is this, from minus 1, minus infinity to minus 1. So minus infinity to minus 1, a of minus n exponential minus j omega of n. This is the other part, this part, because the Fourier transform of this part, putting it in the formula, then simplifying, this is what you get. You change n to minus n, so you replace n by minus n. So limit will change from 1 to infinity, okay, a of n exponential j omega of n, right? That's what you get. Now you can apply the formula only if it runs from 0 to infinity. So add and subtract the term which you get at 0. What do you get at 0? Put n is equal to 0, n is equal to 0, you get 1. So you add a 1 and subtract a 1. So the one you have added, you remove it from here and run this from 0 to infinity. And now you can apply the formula. So apply the formula, simplify it. So it is done on this slide. I just wanted to show you that how it is computed. So the whole thing is done on the slide, that this is what you get. Okay, so you get this. This is for a of n u of n, and this one is for a of minus n u of minus n minus 1. So you get this. So combine them together. The important thing to note here is that there you don't see any j. in the frequency response of a real and even system, you don't see any j. If you replace omega by minus omega, you are going to get the same thing. That is how you check whether function is even or not, because cosine of minus omega is what? Cosine of omega. So this will be an even, a real and even function. A real and even, no matter how complex it is, will give you a real and even with no phase in it. It's just the magnitude, no phase in it. Phase comes from j. If there is no j, there is no phase. Right? So this is a good exercise. You just practice it yourself. And so then is this we already did, right? I did this on the board. This is a moving average filter. So I did this exercise on the board, that how you go and calculate the Fourier transform of this. And I showed you this as well, that this is for pi over 3, m is equal to 3, pi over 3 to pi over 3, and this is how you are going to see the frequency response, and this is the phasor response. And also though it's linear, but it's just doing it. Why? Because you are plotting it from minus pi to pi. And secondly, if there is a change, this in fact is doing like this. So we say 180 degrees phase change. So wherever it crosses 0, you change, the phase is changing basically. Wherever your magnitude is crossing 0, okay, it's a change in phase. Okay? If something coming out positive, 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 will go negative. So that's why you see this. But if you plot it in MATLAB, this is the plot you're going to see. A plot like this. Even in MATLAB, there are two functions. One is angle, the other one is phase. So one of these will only plot a straight line. No matter, it will not break your phase response from minus pi to pi. And this is the MATLAB code. Moving average. It's only if you look at the code, it does nothing. It just take a moving average filter with length with one coefficient only. One coefficient means you are not doing anything. Input is same as the output, so there is no change in the frequency contents. Then a moving average filter with 2 coefficients, with 3 coefficients, and similarly it plots all the. It's a good MATLAB code. You can learn a lot from all the examples which are given here. So as you can see, it's a moving average. Ones will create 1 1 1 1 1. So 1 2 3 10 100, and then you compute the FFTs and then plot the. And this is how you can plot the FFTs, and you can also create an axis which is V, and that'll give you a plot. So you can always plot if you intend your frequency axis to be marked differently. Otherwise MATLAB will just mark from 0 1, it will mark the indices. But if you want MATLAB to mark it differently, you can change your axis. If you look at the plot, so the plot, as you can see, is running from 0 1 2 3 4 5 6 7. So you can basically make it run. It is pi basically. So this is pi by 2. What is pi by 2? 3.12 whatever. So this is 0 to pi and pi to 2 pi. So in MATLAB, if you want your plot to go from 0 to pi, you can change it. Otherwise it will only show you the numbers, the number of points you are taking in the FFT. So this is specially, and this is how it is done, that if there are 256 point FFT, you say I will divide this 2 pi divided by 256. So they go from 0 to 2 pi divided by 256 with this increment. So that will make a V vector. Okay, but it's just a matter of just spending a little more time on this. Just do that to figure out how you can remark your axis from 0 to pi and pi to 2 pi. This is a good example of showing that how the moving average, to take more average of more samples. So basically you will be sampling high frequencies. For example, what if you take moving average of 1000 samples? What will happen? You take 1000 samples, you add them together, divide by 1000, then you move. Again you add 1000, and in this 1000 you are adding 999 of the previous sample. So I can visualize that if I am doing this always 1000 sample, only I am deleting one sample, adding one more sample. what do I expect to get at the output? Almost a DC value, because I'll be getting the same value. Why? Because I'm taking 1000 samples average, then I'm moving and again taking 1000 samples average, where 999 samples are same. Obviously I'm going to see the same thing. So means I will remove all the frequency content. There will be just kind of a DC value. That's what you see. If you increase the number of points in the moving average filter, it will be just a DC value. It will eat up all the frequency contents, obviously. So the averaging is that if you have a higher or averaging filter, is going to eat up all the frequency contents in the signal. The second is another important inverse Fourier transform. An inverse Fourier transform is that usually we say, I have mentioned so many times, that once you are designing, you design a filter in frequency domain. This is the frequency domain. Okay, you always design a system in frequency domain, because at least you give the specification. You say, this is what I intend to design. Okay, you want to design this. So I say, okay, if I make this, then I take inverse Fourier transform. I can always do that because I know the formula. Why to first have h of n and then I take Fourier transform to visualize? Why not? I design, I plot what I want, and then I take the inverse Fourier transform. There is no harm in it, obviously. So I do that. I say, okay, let me take the inverse dt ft inverse, and that formula I know it is 1 over 2 pi minus pi to pi x or h exponential j omega exponential j omega of n d omega. This is the formula. Okay, so now what I am trying to do, that I say, okay, I know what I want to design. Why not I should just take inverse Fourier transform. If I take inverse Fourier transform, I'll get h of n, and once I get h of n, I'll implement it. So this is another approach. So by taking this, I know this is running from minus pi to pi, but it's only 1 from minus omega c to omega of c. So I can easily change the limits, and it is 1. So I change the limit. I say not from minus pi to pi, rather it is minus omega c to omega c, and h exponential j omega is what in this region? It is 1. So I say it is really 1. Okay, and then I take the integral of exponential j omega of n, apply limits, and once I do apply limits, I am going to get this sine omega c n over pi n. So solve this, this is what you will get. Okay, apply the limit, take the this and that, and this is what you are going to get. This is h of n. Okay, this is h of n. This is a sinc function. Okay, if you plot this sinc function, we know that sinc will appear like this. This is a very good example of an IIR system. This is an IIR system. Sine omega c n over pi n is an IIR system. If you look at this, this is real and even. H exponential j omega is real because it is 1, and it is even because it's same on both sides. H of n is also real and even, right? This is real and even. So this is, now the question is, oh, I really get an IIR system which is real and even. So what is the significance of something real and even? There will be no phase distortion. If I implement this system, there will be no phase distortion. Right? So this is really an ideal system. We call it an ideal system because h of n sine omega c n over pi n is an ideal system for several reasons. One reason is it perfectly zeros the unwanted frequencies. It passes the wanted frequencies as is, 1, no phase. It is not going to change the phase of my input. This is ideal. If somehow I can get something like this, this is the ideal. Then there is no need of DSP. Basically, if something like this is realizable, there is no need for DSP. But the problem with this h of n is that you cannot put it in a difference equation form. An IR filter got to be realized if you change an infinite impulse response into a difference equation. Only then you can realize an IR system, that it got to be represented by a difference equation. This system cannot be represented as a difference equation. So means you use convolution summation. Anything which you cannot describe using the difference equation, you implement it as a convolution summation. If you apply it as a convolution summation, the same problem. It is non-causal and it requires all the future samples and all the past samples to compute one output sample. Okay, just remember that h of n for negative indices, these are in fact impulses. Okay, even if you have in your impulse response anything at -1, what does it mean? Y of n plus 1. What if you have at -2? Yn plus 2. Okay, so if you have all these in the impulse response, it means you require all the future output samples, the input samples to compute a current output sample. So this is a non-realizable system. Okay, you cannot realize it because of these two limitations, that it is an infinite impulse response, it cannot be represented by a difference equation. A convolution summation will require all the future samples to compute the current output sample, and which is obviously not possible. So this is now out of means ideal is not possible. So this is where the DSP starts. If ideal is not possible, how close can I get to this ideal? Okay, so now the game is that okay, ideal is not possible, it is proven, let's try to get closer to this ideal. So what is closer? I really want something which just cut off my unwanted frequencies. You cannot get that. They will, as you have seen the filter which I showed you, there would be something like it will never be that something which just takes away the unwanted and gives you the wanted. No, it's not going to happen. You will always get a transition and something undesirable coming into yours, always. So this is that you cannot get to the ideal. Ideal requires something which is non-realizable. So now the DSP tries, all the DSP what we are going to study in this course, the first part of the course, will try to get you closer and closer to an ideal system, a realizable system which gets you closer to ideal, but you will always have transition and you will always have ripples. What a ripple will do to your wanted frequency? If it is 1.2 and this is 0.98, it means this particular frequency will be amplified a little bit, right? This particular frequency content will be multiplied by not 1 but 1.2, so it will be amplified a little bit. What about which is 0.98? It will attenuate it. So there will be some undesirable effect on the frequencies which you want to pass unaltered. There will be effect because there are ripples here. And what will happen here? The unwanted frequency will also get into which you don't want. Okay. Now it's up to you that how much do you want to spend. So there are now techniques. People have tried different things. The entire literature now revolves around that how closer can you get to this spending minimum number of computation. Okay. So this is we'll study about this more, but just register this point that you cannot get to the ideal. The entire DSP is now trying to get to the ideal by spending minimum number of computation. Okay. So here is a simplest way. A simplest way is I say I know I cannot get to the ideal, but I really like this thing. Why? Because it is real and even. So I like it because I know if something is real and even, I can chop it off and I can shift it to make it causal. So it will have a linear phase response. So I say I really like it because it is real and even. Okay, I cut it here, I cut it here. Okay, I say okay, I cut it here, I cut it here. Once you cut it means you are not considering these samples, and then I shift it to make it causal. So this is something good. Obviously the effect of chopping is that you will not get something which is ideal. So the effect is that if you do that, this is the effect, and this is will help you to understand the chemistry of signal processing, that you say okay, I cut 5 samples from here and 5 samples on the other side, 5 here, 5 here. So I say okay, what about if I take from -5 to 5? Okay, this is what you are going to get, and dotted shows the ideal. So you are not going to get the ideal, but you see these ripples. So this large ripples, you see the transition, and not very sharp transition. You say no, really I don't like it because it will get all these frequency contents with these magnitudes. It is going to attenuate all these frequency contents with this much magnitude. Is going to amplify my wanted frequencies like this, attenuate my wanted this. So this is how it is going to shape my frequency spectrum. So I am willing to spend more. Say okay, spend more. You take 9 samples on both sides. You see the transition is improving. You even spend more. You even spend more. So you see, look at this. So you have usually transition is something very critical. You say, this is good. Still there is some transition, but it's very close to what you want. But look, 35. 35 on this side, 35 on that side, 70 plus 1 in the center. So it has 71 coefficients. So what does it signify? Cost. 71 multiplication and 70 addition to calculate every output sample. Right? A one filter will cost you 71 multiplication. So a signal, 71 multiplication, 70 addition, you get one output. Then again you do all that, you get again another sample. So this is the cost. But this is a good exercise to show you that this is how you can always pay more. Definitely techniques do help. By spending these many and using some better techniques, not just cutting off, using some better techniques, may give you this type of a response in fewer number of coefficients, maybe 20. It says just take 20 here, but don't just cut off the samples. Do this technique, do this trick, do this trick. So now there are tricks which people have devised to get you a response which is closer to ideal and spending less number of coefficients. So that's how people, once they publish, this is how the judges say, look, I have devised this technique to design a filter which takes only these many samples and it gives you better results, or better than what you otherwise get, which is the crudest way, just chopping off the cutting the sink. That is the crudest. Obviously that is the crudest. If you did nothing, you said okay, this is saying let me just take these many samples. But so then the techniques, there are several techniques, we learn about those techniques which says okay, do this, do that, and they'll help you to design an FIR filter. It's a finite impulse response because of the finite nature of the impulse response. Another,
this will also create a delay of 35 milliseconds.
Oh yes.
Ultimately, the buffer size for the main signal will be the double of.
Yes, because the length of this filter is 71. So it means length 71 means 1 x of n and 70 x of n minus 1 minus 2 minus 3 up to x of n minus 70. That is what will require you to implement this system. And once you get a full overlap, how many samples do you need? First time you see a full overlap is once you have 71 samples, input sample. So 70 samples will be garbage, the partial overlap. Remember, this is your impulse response, and signal is you started and you just keep moving. And once you have your pipeline is filled, all the delay line is filled, only then you start getting the good samples. There will be a delay of 70 samples. Yes, there will be a delay of 70 samples, which is inherent. I already told you earlier in the course that the delay is inherent in signal processing because it's a processing delay and the system requires the previous sample to compute an output sample. That's why there will be delay. Another perspective is that okay, this is a low pass filter, but interestingly any kind of filter can be designed using a low pass filter, and I'll show you how. For example, you say I want to design this filter, and which is what filter it is? A high pass filter. Okay, and remember it's going to be on the both sides. And do remember that if it is a real system, h of n is real, it is always going to be symmetric. If something is not real, something is not symmetric, by looking at the Fourier transform I can tell that its h of n is complex. This is important, that it's not that you always design h of n real. You may want to in some applications you may want your h of n to be complex. It may be one when you want your h exponential j omega not symmetrical. Once it is not symmetrical, h of n will come out to be complex, no problem. Okay, no problem. You have an h of n which is complex or what? So h of n may be complex, but we will usually, at least in this course, deal with real h of n. So this, if you look at this, you say, oh, I think I can really design a low pass filter and get a high pass filter. How? I say I subtract a low pass filter from all 1. Okay, what will I get? If I subtract this minus this, do I get this? Yeah, I get this. Okay, because this minus this will give me this 1 minus this in frequency domain. I say 1 minus h low pass exponential j omega is in fact h high pass. What is the inverse Fourier transform of 1? It is delta of, it is an impulse at the center, minus h of low pass of n, which is a sink. Remember, h of low pass n is a sink. So it tells me that by inverting all the samples of h of n, inverting means multiplying all the samples by -1, all positive becomes negative or negative becomes positive, and then subtracting, so doing this and adding 1 at 0. Delta of n is 1 at the 0. Delta of n is this. Will make a low pass filter a high pass filter. Similarly, you can think about designing a band pass, a band stop, or any kind of filter by manipulating a low pass filter. Okay? So the important is that you need to know how to design a low pass filter, and the others will follow. So then this is another important slide. You need to know all these Fourier transform pairs. Delta of n Fourier transform is 1. If you have a constant sequence of 1, usually the summation sometimes is confusing to student. It only says that 1, the Fourier transform of 1. What is 1? A constant 1, means from minus infinity to infinity 1 1 1 1 1 1 1 1 1. Okay. If you have a sequence which is all ones, so this is all ones. Okay. From minus infinity to infinity all ones. Its Fourier transform is really delta of omega at 0. This is an impulse in frequency, an impulse at 0. But we know Fourier transform is periodic over 2 pi, remember? So you are going to see the same thing at every 2 pi. This is 2 pi delta omega. अच्छा, अब इसकी वैसे let's look at the significance. This is important. What is this? It's just a DC value. Is there any frequency in it? There's no frequency in it. Okay, it's just a DC value. It's all 1 1 1 means it's just a DC value. There's absolutely no frequency in it. I expect this not to have any frequency content in the frequency response. Once I plot its Fourier transform, I don't want to see that it has any frequency, right? It just has a DC value. DC value is what? 0. So an impulse at 0 means that it is only a DC value. There is no frequency in it. Okay, so that's why you see a 0. 2 pi is also DC, minus 2 pi is also DC, 4 pi is because it is periodic. But looking at this, if I see an impulse in the frequency response at 0, it means it is only a DC value. There is no frequency in this signal. And 2 pi is coming because of the formula. In different books you will find different formula. Either you have to put this 2 pi here or the 2 pi there, but this 2 pi is coming from the formula. It is a bit confusing, but the 2 pi is coming from the formula, which says this DC value is 2 pi, it's not 2 pi. So divide, if you look at the value, just divide it by 2 pi. That will give you a better indication of what it is in the time domain. So this is what you get, and that's why it is written like this. 1 2 pi k minus infinity delta omega plus 2 pi k. It is everywhere at 2 pi minus 2 pi 4 pi. I said the next is even more interesting. Exponential j omega naught n. Okay, it has only one frequency. Exponential j omega naught n has only one frequency. What frequency it is? N omega naught. It has only one frequency, that frequency is omega naught, because cosine of omega naught n plus j sine of omega naught n. So another interpretation of the Fourier transform is, it tells you that what frequency exponential is there in the signal. A very simple interpretation of the frequency response, that it tells you, and this is important because that will clear your ideas about negative frequency and positive frequency. It's not about frequencies. The Fourier transform formula tells you that what type of complex exponentials are there in the signal. Here, how many complex exponentials are there? 1. At what frequency? Omega naught. So if you plot the Fourier transform, it will say there is only one frequency content at omega naught. Okay, so its Fourier transform is 2 pi is coming again from the formula. Okay, S is only one frequency content at omega naught. So this is again important in not only its significance is more important. That the significance is that this tells you what Fourier transform is. Fourier transform will tell you that how many complex exponentials are there and what frequency complex exponentials are there in the signal. Okay, if its omega naught is 0, exponential of 0 is 1, so it is a DC value. That's why you see the same at 0. What if you have minus here? Same at minus omega naught. And this will help us to understand the cosine of omega naught. And how many complex exponentials are there in a cosine? 2 complex exponential. One at j omega naught and other one is at minus j omega. So you are going to see 2 of these. Okay, so you are going to see 2 of these if you say a cosine omega naught minus omega naught. Okay, so that's what the Fourier transform is not indication of what frequencies are there in your signal. It's not. Fourier transform is that what complex exponentials are there in your signal. So this is the difference. There are transform which is called cosine transform, sine transform, this transform, that transform. That tells you that these cosines are there in your signal. But a Fourier transform is that what type of complex exponentials are there in your signal. And that's why once you put cosine, you are going to see two of these impulses. If you put sine, again you are going to see 2 of these. Okay, if you put an exponential, you only see 1, because there is only one complex exponential. So, and then the confusing part is that you are going to see these at every 2 pi. So you see only one delta omega minus omega naught, and then plus 2 pi k means it is everywhere because it is periodic over 2 pi. So that's why you see this summation. Okay, so cosine जी नहीं देखिए जो this does not care whether it is periodic or non-periodic. It assumes it is just a signal which runs from minus infinity to infinity. ठीक है, whether it is cosine, it is exponential, it is a, for example, a of n, u of n, it is not periodic, right? A of n, u of n is not periodic because it's just an exponential. So the formula does not care whether something is periodic or not. Okay, the Fourier transform formula is Fourier series which says if it is periodic then you can do this. Okay, it is not Fourier series, it is a Fourier transform which says anything it in time domain you can figure out how many complex exponentials are there in this particular signal. Right? If you find 2 of these, one on this side and another on this side, you can reiterate or rephrase the sentence. You say how many cosines are there, because a point here and a point here means that the cosines, right? The cosines are there. So you say how many cosines are there. If a signal is real, its Fourier transform for sure is going to have a point here and a point there. Means that there will be cosines in a real signal. Achha, isse, what really we infer from this is, once you look at the Fourier transform of any x of n, it will have not impulses but a spectrum, something like this. Okay, this is a spectrum. It means that this signal has all these complex exponentials. Okay, from 0 to pi and minus pi. And this is important, that any signal can be broken, so to say, into infinite many complex exponentials of different magnitude. This is again very important. The Fourier basically concluded this, that any signal, whether periodic or aperiodic, can be broken into infinite many exponentials. And that's what Fourier transform is. It only tells you that how many complex exponentials are there in the signal. And that is what frequency is. You say, okay, this signal, looking at this, I know these are the complex exponential. If appearing on the both side, means these are the cosines. Okay? So I say, okay, these are the frequencies in the signal. The frequencies in the signal, and this is an interpretation. Why? Because Fourier concluded that this is really true. And we have seen this exponential j. This is, though it's a mathematical formula, it tells you something about the frequency contents in the signal. Right? That's how a signal basically consists of varying different frequencies, and usually all frequencies. Once you look at a spectrum, it means it has all the frequencies. If it is not an impulse, it means all the frequencies are there. Some are smaller frequency contributing less, and some are bigger frequencies contributing more in the signal. So, but the formulas are important. This formula, this formula, this formula. U of n is 1 over 1 minus exponential minus j omega plus pi, and this is coming. So you see, basically this is an impulse at 0, impulse at 2 pi, impulse at minus 2 pi, a unit step function. The reason of seeing these type of terms in a unit step function is because it is not absolutely summable. The Fourier transform says that you can only compute a Fourier transform in closed form expression if your h of n is or x of n is absolutely summable. Because it is not absolutely summable, I'll not get into the proof of it, but because I'm just giving you a reason that because it is not absolutely summable, you cannot put it in a closed form. What is a closed form? A closed form is this. This is a closed form expression. Okay, which does not, you don't see this. You don't see a summation of k minus infinity to infinity, and you know. But all these are, this is absolutely summable. So you see a closed form. This is not absolutely summable. So you keep seeing the summation. Summation is going to be there in the expression. So summation is going to be there in the expression. Summation is, because cosine of omega naught n is also, you cannot just take the absolute value and sum them. So it tells you that, oh, I think it is not summable, that's why you are seeing a summation. A summation will only go away if your sequence is absolutely summable. A good example is a of n u of n. I have already computed its Fourier transform. It is 1 over 1 minus a exponential minus j omega. Okay. Now, knowing this, knowing the properties. So in exams, usually you are allowed to, I call this a cheat sheet, that you are allowed an A4 paper sheet where you can write whatever you want to write. You can write all the formulas, and you can miniaturize your sheet, put whatever you want to put. But you can start making your sheet where you put all the properties which are important, and in a small portion you may also want to put all these pairs. So usually we ask questions where you are given something, you need to apply properties and these formulas to find the Fourier transform. For example, I ask you to compute the Fourier transform of 0.5 n minus 2 u of n minus 7. Okay. For example, looking at this, I know that either I can use the formula. It will be very confusing to use the formula because your summation will be running from 7 to infinity, and so it's better that you apply properties. So the property, I know that there is a property which says if xn minus d is Fourier transform is exponential minus j omega d n. So if somehow I can put this expression in this form, where every n appears with n minus 7, I can just use the formula. So how to make this expression look like that? You say 0.5 n minus 7 plus 7 minus 2, right? U of n minus 7, and then it is 0.5 7 minus 2 is raised to the power 5, and 0.5 n minus 7 u of. Now you are all set to use the formula. You say, I know the Fourier transform of 0.5 n u of n. It is 1 over 1 minus 0.5 exponential minus j omega. We know it's a of n u of n. Okay, and now use the property. You say, using this time delay property, if the Fourier transform of this will be what? 0. This is constant, so you don't worry about that. Exponential minus j omega d minus j omega 7 and x exponential j omega, right? So the combination of the properties and the pair can help you to answer questions like these. Several at the end of the book. Okay, they may put, okay, what do you do if you have minus here? You know, let's say this 5n minus 2 u of minus n minus 7. You remember it's a flip in time, is flip in frequency. So you can just make use of that. You say, I will first compute a of minus n, u of minus n. By, I say, if I know a of n, u of n is 1 over 1 minus a exponential minus j omega, then this will be 1 over 1 minus a exponential j omega. And then I use shift in time property. I'll rewrite this minus n in bracket. If it is minus 7, so I write u of minus n plus 7, right? So this is, so make every n appear as n plus 7 and then use that property, right? So there are several questions. We'll try to arrange a tutorial hum kar sakte hain, like a session where not the regular class hours, where we just solve few questions from end of the chapter. Okay, so you may plan that. So those of you who really want to go through some of those questions, usme will be not in the class timing, so we'll just run a tutorial session where we will only solve problems at the end of the book, so that you really understand. We'll also give you assignments to practice, but this is important. All these pairs are important from several perspectives, though these are just formulas, but their significance is that, especially in the book, you will find the book plots the magnitude response and the phase response of 1 over 1 minus a exponential minus j omega. Okay, so you look at the plot, you will find out the magnitude is a low pass, but the phase is nonlinear. They'll help you to comprehend that an IR filter will have a nonlinear magnitude. And this is also an important slide which shows you, because we'll be using several terms in this course: analog frequency, okay, discrete frequency, and MATLAB index. So you need to correlate all these together. There is yet another, which is F, frequency in hertz. Usually we are used to frequency in hertz. Okay, in real life, in real signal, analog signal, frequencies are in hertz, kilohertz, megahertz, this hertz, that hertz. So we know that capital omega is 2 pi f, right? So you can always go from hertz to radians per second. So radians per second is simple. Omega s is radians per second, and it is 2 pi f. F is frequency in hertz, or sometimes you write 2 pi over t. So 2 pi over capital T, t is the time period, right? जी
नेटवर्क में जब भी हम किसी लिंक की बैंडविड्थ की बात करते हैं तो हम डेटा रेट को बैंडविड्थ क्यों बोलते हैं? मतलब 2 megabits per second the bandwidth of this link. There is no
दरअसल ये these are like the terms, they are used. Once you talk about a communication wireless link, you talk about hertz, very different. Once you talk about the throughput, it is called the bandwidth in terms of bits per second, very different. They are not related. Ji? Yes, I am saying it, this basically it's an abuse term, so to say. The bandwidth is an abuse term. ठीक है, bandwidth of a link you say, but it is in some form related to the actual bandwidth of the channel. ठीक है, अब information coding you should learn the channel capacity theorem, that if you have this much bandwidth it can only support this much data rate with the signal to noise ratio, you know. So though it is indirectly linked with the bandwidth, the bandwidth is the band of frequencies in which you can transmit. ठीक है, data rate is related to that. How it is related to that? If you have a signal, ठीक है, आप signal generate करें 1 and 0, 1 0 1 0 1 0. Worst case is, let's say you say 1 kilobit per second. What is 1 kilobit per second? 1 kilobit per second, in 1 second a signal can change 1000 times. That is 1 kilobit. So you generate a worst case scenario which is, it is always changing, 1 and 0 1 and 0 1, and this is the worst case. Plot its frequency response, just take its Fourier transform. Okay, and 1 kilohertz will be a frequency band, ठीक है, because it requires 2 sample. I think it will be 1 kilohertz, almost equivalent to 1 kilohertz or 2 kilohertz, I don't remember, but it is related to that. Why? Because no, it will be 1 over 2 kilohertz. Why? Because look, this is 1 cycle. Okay, a 2 bits is 1 cycle. So this is how it is related. You say 1 megahertz, 1 megabit per second. What is 1 megabit per second? A signal is changing how many times? 10 raised to the power 6, worst case scenario, 10 raised to the power 6 times in a second. So there are how many cycles? If a change is a cycle, so there will be half the number of cycles. So this is how that is related, but it's not a direct relationship, but there is a relationship, and that's why it's an abuse term, but it really means an indirect relationship of what you say throughput to a frequency. No direct relationship, because then there are other complex waveforms, but from signal processing perspective you don't talk about a bit per second. Okay, so always frequency. And this is important, though I have already told you this, half the sampling frequency is pi, and the sampling frequency corresponds to 2 pi. And if you take FFT in MATLAB, n by 2 corresponds to pi, and n it says static, and static says MATLAB never gives you an n, it only gives you from 0 to n minus 1. Why? Because it repeats itself. Whatever you get at 0, you get the same thing at 2 pi. So MATLAB will not give you capital N. If you take the Fourier transform, it will not give you capital N where it repeats. It will only give you 0 to n minus 1. Right? So these are the relationship of the frequency axis, analog frequency. Again, usually we would love to see frequencies in analog domain because we have a direct correspondence with this frequency. Okay, it's a 6 megahertz, 7 megahertz. So usually once you plot, even in MATLAB, a discrete frequency axis, I've already shown you how to change the frequency axis. It's a simple change, and change is you say capital N corresponds to f of s. Okay, so one sample corresponds to f of s over n. So a simple relationship like this. So you can always switch the axis. You can actually label the axis in hertz instead of indices. If you don't do that, MATLAB will label it in indices. So I quickly show you an example. You say we already have an x. No. Let me just generate an x, 1 2 3 minus 1. Okay, if you take FFT of x and you plot it, stamp it or plot it, so MATLAB is going to so this is, I'll show you the indices. 0, I'll start MATLAB indices start at 1, 1, 2, 3 and 4. These are the 4 samples of the frequency response. Okay, so I'll show you the indices as 1, 2, 3, 4, 5. So this is not very convenient. You're not able to understand because you have to correspond an index to a frequency. So you can always change the axis, label the axis in hertz. Okay, and that I'll spend more time on it next time. But this brings us to the end. Ji.
Fourier transform when किसी टाइम डोमेन में किसी सिग्नल कैरेक्टरिस्टिक को स्टडी करना मुश्किल है, तो इनसाइड उसको दूसरे डोमेन में स्टडी करने के लिए ये फूरियर सीरीज का क्या रोल है?
जी, we'll spend some time in Fourier series. अच्छा, Fourier series जो है a very important concept in signal processing and signal and system from understanding perspective. अब Fourier ने देखा कि any periodic signal can be broken in terms of complex exponentials. Okay? He says, okay, if this is the signal, I can really, or in terms of cosines and sines, or in terms of cosines. ठीक है, Fourier said any periodic signal can be broken into cosines. ये उसकी significance है. ठीक है, so if it is a cosine, there is only one cosine in it. But if it is a square pulse, let's say Fourier का we'll spend time learning about, because ये पूरा chapter है इसमें, we'll spend some time, but quickly to answer your question, let's say you have any periodic signal, ये है आपका, ठीक है. Fourier का जो ये पेपर था ये रिजेक्ट हो गया था. People thought he is crazy, that how can this be possible. Fourier said any periodic signal can be broken into sines and cosines. ठीक है, the top most mathematician Lagrange and others, they rejected his paper. He said it's a stupid thing to say. He said any periodic signal can be broken into sines such that once you add all the sines you will get the same signal back. Okay, no matter what type of signal it is. For example, you can generate you just draw anything which is periodic. Something he said there will be a cosine of this frequency, which is the fundamental frequency. There will be a cosine of twice this frequency, which is, there will be a cosine of 3 times this frequency. And he proved that if you add these together, you get the signal. Okay, so this is what the Fourier series is, simple in terms. So लेकिन उसकी obviously we don't deal with periodic signals, we need to really, तो उसमें वो है कि then उसमें हम उस तरह relate करेंगे इन दोनों चीज़ों.